Hello again, everyone. So, as I maybe mentioned in the classroom, I thought we'd try something a bit different today. So, what I'm going to do is talk through the halogenoalkanes topic, chat you through the different things that I think are important, or all of it really, and then I'll set some questions based on those ideas. So, to start with, you've got three different types of halogenoalkane. You've got a primary, which is given that symbol sometimes. You have a secondary, which is given that symbol sometimes, and then you have a tertiary, which is given that symbol sometimes. So an example of a primary halogenoalkane might be 2-chloroethane, something like that. So the carbon to chlorine bond, the carbon part of that is attached to one other carbon. You've got a secondary halogenoalkane where the carbon attached to the halogen is attached to two other carbons. So this is an example of a secondary halogenoalkane. And then a tertiary would be the carbon attached to the halogen is attached to three other carbons. So ends up looking something like that. So primary, the carbon attached to the halogen is attached to one other carbon, secondary attached to two other carbons, and tertiary attached to three other carbons. Now, halogenoalkanes undergo lots of different reactions. They are quite reactive, and the reason they are very reactive is because if I draw, I've done chlorine previously, so I might as well do the same thing again. So the reason that they are so reactive is because of a permanent dipole that exists between the carbon and the halogen. So the halogen has a stronger pull on the electrons in this covalent bond, which means it pulls them closer to itself. It's better at pulling the electrons than carbon is, and so carbon ends up becoming partially positive, and the chlorine becomes partially negative. So those electrons are slightly closer to chlorine than they are to carbon. Because of this, then, you have what are called nucleophiles. So nucleophiles are species with that contain a lone pair of electrons. So you think of them as being electron rich because they have a lone pair of electrons, and what they can do is they can go in and attack that delta positive carbon because it is lacking electrons, and that's the main reason then why halogenoalkanes are so reactive, because of this permanent dipole. So some examples of nucleophiles that might attack, there's three, I'd say, really important ones that you need to be able to give the mechanism for. So the first, I'm going to stick with chlorine again. So chloroethane here, let's say we added sodium hydroxide to it, and the sodium hydroxide is aqueous, which means it's dissolved in water. What will happen is the hydroxide ions, which have there's a lone pair of electrons on the oxygen, so these two dots represent a lone pair. This negative is a negative charge. The lone pair of electrons will go in and attack the delta positive carbon. So lacking electrons, lots of electrons, goes in and attacks. It's important that your arrow goes to the carbon, not to this bond or something else. It needs to go to the carbon and be really clear. And then as a result, the electrons in that bond get kicked out onto the chlorine, which is the delta negative part, and we get what is called a nucleophilic substitution reaction happening, where we make an alcohol. So the OH minus substituted for the chlorine, so chlorine gets kicked out, we have Cl minus being left over, and the OH has taken its place. So this is a nucleophilic substitution reaction. Sensible name, nucleophilic, the nucleophile, substitution, because the nucleophile substitutes, and you get OH substituting in. So that's one version. I might change the molecule up now, so I might do, let's do bromine as another example. Another example of a nucleophile is cyanide, so Cn minus. To do this sort of substitution, you could add KCN, aqueous, or it could be sodium cyanide. Either could be true. This chemical looks like this. So it's carbon with a triple bond to the nitrogen, and then the carbon has got a lone pair of electrons as well. So what happens, same again, delta minus, delta plus, goes in and attacks, specifically going into the carbon, and then kicks the electrons in these bonds out, so the electrons in the bond move on to the bromine. So we end up getting substitution, we get C, I'll draw it all out, triple bond N like that. Don't know why I added a bond there. So this is quite a useful reaction, particularly when you get into A2, because it's a way of making the carbon chain longer. So if you want to do that for whatever reason, tends to be the sort of thing, or reagents that you use, and then Br minus as the side product. Final type, which you may be asked, unlikely, but you never know, is, let's imagine we've got halogenoalkane again. You can react it with ammonia, so NH3. The reason being is because ammonia has a lone pair of electrons again. This is something that doesn't have a negative charge. The mechanism is ever so slightly different, but it may come up. So what happens? Delta plus, delta minus, goes in and attacks specifically to the carbon, kicks the iodine out. So it would just be ammonia that you'd use in this, NH3 being used. This gives you this as a product. Now, nitrogen is able to form 3 bonds. So here it's stable, here it's got too many bonds, it has a plus charge, so it's currently not stable. The other side product that you'd have would be I minus. I'll just keep that there for the moment. Now you'd want the ammonia to be in excess so that we can do this. So you've got NH3 again. What happens is another one comes along, attacks the hydrogen, and the electrons in this bond go and stabilize the nitrogen, so that we end up, I'm going to scoot it all around, so that we end up with NH2 like that. So the nitrogen's now got 3 bonds, 1, 2, 3, it's stable, and the other side product that you then have, so this NH3 also picks up this hydrogen, so it's now NH4 plus, and it joins with the I minus, NH4 plus, I minus, gives us NH4I as another product. So that one is slightly more complicated. The other two are nice and straightforward, I would say, but hopefully you can see the pattern, especially at the start bit, where the same thing happens every single time. The only thing different really about this one is this step, is there's one extra step to the reaction. Okay, so the next part of this topic is then looking at the relative rates of reaction or nucleophilic substitution for different types of halogenoalkanes. So we've got fluoromethane, chloromethane, bromomethane, and iodomethane here. The dipoles would be delta minus, delta plus, and the same way around for each of them, so the halogen's always the more electronegative of the two. Now, fluorine is the most electronegative element, so it has a very, very strong pull on the bonding electrons. So they would be all the way over here, which means that would be very, very positive, if you want to think of it that way. The chlorine's slightly less electronegative, so it's going to be far, but not quite as far. Again, bromine is slightly less electronegative again, so you can see fluorine's pulled them all the way over, so this is very positive. Chlorine's pulled them over, but not quite as far. Bromine less again, and then iodine even less again. So if we were going to predict based on electronegativity which ones of these would be the fastest at doing this, so at performing nucleophilic substitution, I hope you agree with me that actually we would think in terms of electronegativity, this one would be first, this one would be second, this one would be third, and then the iodoalkane would be the fourth. Because this is the most delta positive carbon, it would be easiest for the nucleophile to go in and attack this one, then this one, then this one, and then this one. So that's, if we were going to predict the relative rates based on electronegativity, we would rank them this way. Now, another way we could predict the relative rates of the reaction is by bond strength. So if I said to you the carbon to fluorine bond was the strongest bond, followed by the carbon to chlorine bond, followed by the carbon to bromine bond, and then followed by the carbon to iodine bond. So this one's strongest, then that one, then that one, then that one. We would say that this is hardest to break and therefore the slowest rate of reaction, followed by this in third place, followed by carbon to bromine in second place, and then finally carbon to iodine, because it's the easiest bond to break, would have the fastest rate of reaction. So we have these two factors which we need to decide which one is more important. The one that has the biggest influence is actually the bond strength. So biggest influence is bond strength, and therefore actually the relative rates of reaction are dictated by the bond strength. And you need to be able to argue both sides, but then be able to state that because this has the bigger influence, the relative rates of reaction are in this order. So carbon to iodine bonds would break fastest, then carbon to bromine, carbon to chlorine, and then carbon to fluorine. Okay, so that's relative rates of reaction. Say this one has the biggest influence. Another thing we need to be able to do is test for the different types of halogenoalkanes. So test for a fluoroalkane, a chloroalkane, a bromoalkane, or an iodoalkane. So let's imagine we've got 4 pots. One of them has got the fluoroalkane in it, so CH3F. One of them has got CH3Cl in it. One of them has got CH3Br in it, and the other one has got CH3I in there. So we need a test to, if we didn't know what was in there, to determine what was in each of the containers. So first thing you would do, step 1, is to add aqueous sodium hydroxide to each of them. So step 1, NaOH aqueous to every single one of them, and as we mentioned previously in the video, what that will do is you'll get nucleophilic substitution happening. The OH minus will go in and attack the halogen, kick it out, and we'll get an alcohol forming. But more importantly, now inside the solution we'll have I minus ions kicking around. So CH3OH will be in there, but also the halide ions. So in this case it would be Br minus. In this one we would have CH3OH and Cl minus, and in the top one CH3OH and F minus in there. Now, when you were in year 10, you will have looked at a test for these different ions. The test is to add silver nitrate. So silver nitrate, which is AgNO3. You would want to add a little bit of nitric acid as well. So this is step 2. So add some nitric acid as well to neutralize the solution. So that's HNO3. If we do the same for each of those, if we've got, let's start with the bottom one. So if we've got iodide ions present and we add silver nitrate and nitric acid, we'll get a yellow precipitate forming. So precipitate is just the fancy way of saying that a yellow solid will be made inside the liquid. For bromide ions, we'll get a cream precipitate. Sometimes it's called a pale yellow precipitate. I think cream's fine. And then chloride ions, you'll get a white precipitate. So a white solid will form inside your liquid. If we've got fluoride ions, you get no precipitate. So nothing happens. So that's a way of differentiating between the three. Now, if you've ever done this in practice, it's quite hard to tell the difference between something that's cream and something that's yellow. It's often easy to decide which one the white one is, but cream and yellow is sometimes a bit more difficult. So you can do a supplementary test, which will be your third step, which is to add ammonia, so NH3. If you were to add ammonia, the ammonia would be trying to dissolve these solids that get made, so the white precipitate, the cream precipitate and the yellow precipitate. The yellow precipitate, if I add ammonia, would be insoluble, so it would be impossible to dissolve it. The cream precipitate would be partially soluble, so some of it would dissolve but not really all of it. And then the white precipitate would be completely soluble in the ammonia. So that's sort of like a supplementary test that you can use. So far we've looked at nucleophilic substitution reactions, the relative rates of those reactions, and how to test for the different types of halogenoalkanes. Another reaction that halogenoalkanes can undergo is called nucleophilic elimination. So rather than substitution now, so rather than something substituting because of a nucleophile, something is being eliminated because of a nucleophile. So in order to do this, let's imagine, let's do this as my halogenoalkane. Okay, so I've got 2-bromobutane. I'm going to add sodium hydroxide again, but this time it is going to be in ethanol. So rather than dissolved in water, I've dissolved it in an alcohol. It could be another alcohol, it tends to be in ethanol. If we do that, rather than having nucleophilic substitution, you actually get elimination. So what happens is the bromine becomes eliminated and a hydrogen on one of the carbons next door. So there's 2 possible products for this. We could get, let's imagine we have that bromine gets lost and one of these 2 hydrogens. So on the carbon next door, it would look like this. So we've lost the bromine, we've lost this hydrogen. Let's finish off these hydrogens here. A double bond has formed, so we've made butanene. The other option is, yes, to lose this bromine again, but to lose one of these 3 hydrogens. So let's imagine we lost this one, we would end up with but-1-ene like that. So there's two possible products for this type of reaction. You don't need to worry about which one forms more, which one is the major product, which one is the minor product. Just be able to predict what the two products would be. So if we do one more example, let's say you've got let's do a tertiary halogenoalkane. Again, it doesn't have to be bromine, so I've just picked bromine. Let's do chlorine instead. So I add sodium hydroxide. It's in an alcohol, so typically an ethanol. The chlorine will be eliminated, and then on one of the neighbouring carbons, so this one, or this one, hydrogen will be lost. In fact, in this molecule here, there's only one possible product, because no matter where you lose the hydrogen, you're always going to get the same molecule being formed. So you can check it if you want to, but you're always going to get this molecule being formed, which is methylpropene. So if I was to lose this hydrogen and the chlorine, the double bond would be there, it would still be methylpropene. Double bond there for the last version, it would still be methylpropene. So in each case, we'd only ever get methylpropene for that reaction there. So what are the main differences between nucleophilic elimination and nucleophilic substitution? In nucleophilic elimination, we need to reflux. So in both these situations, we'd need to reflux. In sodium hydroxide, which is dissolved in ethanol, in elimination we get alkenes as product. In substitution we get typically an alcohol as a product, or if we use another nucleophile we get something different. In substitution, so if I put N substitution down here, so you still need to reflux in substitution, which is probably something I forgot to mention earlier. So you reflux in, say, NaOH, which would be aqueous. So the main difference is the fact that in substitution it's aqueous, in nucleophilic elimination it is an alcohol. Now I've mentioned the word reflux a couple of times here, so you need to reflux in this type of reaction and in this type of reaction, but what on earth does reflux actually mean? So let's imagine we've got my reaction mixture here. So let's just pick one of these. Let's imagine I've got 2-bromobutane and I've mixed it with sodium hydroxide in ethanol and put it in that pot. In order to get the reaction to work, I need to heat it up. So I need to add heat, put a Bunsen burner underneath and heat it up. The problem with just heating it up normally is that some of it will turn into a gas, so it will evaporate and it will escape out through the top. So what you do when you reflux is you attach what is called a condenser to your reaction mixture, and you'll have water coming in and water coming out. So I always forget which way round they are. Give me a second. I would imagine the water will be at the bottom coming in. I could be wrong. So yeah, water in through the bottom from a tap, and then the water will come back out at the top. And with this condenser then, it's a bit like distillation that you'll have done in year 10. It's the same condenser that's used, you just flip it round. It's got an inner tube and an outer tube. So the outer tube is where all your cold water is going to be travelling from the tap, so along this outer tube. And then that means as you heat up your mixture, the bits that evaporate are going to travel to this condenser, and they're going to cool back down, and then they're going to fall straight back into your mixture. So it stops things from being lost, but allows us to still heat things up. You wouldn't typically put a lid on top, because you can imagine if you're heating this stuff up and it's all turning into a gas, the pressure is going to start increasing, and the lid is going to pop off eventually. So you wouldn't put a lid on this, and it's actually, if they ask you to draw it, make sure you don't put a lid on top. The final part of the topic is talking about the uses of halogenoalkanes. So one major use is as a solvent, and the other major use is in anaesthetics. So anaesthetics is more brief. Let's start with that one. Anaesthetics, for example, what's called the Mickey Finn drug is called 2,2,2-trichloroethane 1,1-diol. There are other examples as well. So anaesthetics is one branch where halogenoalkanes are used. The other one, that maybe one we're going to focus on more, is in solvents. The reason there's used in solvents is because if I draw an example of one, so here's a halogenoalkane. You've got the dipole, delta minus, delta plus. This region is what's called a polar region. So it has polar interactions. So it will interact really well with polar solvents. And then this top region here is non-polar. So there's no significant dipoles. There's no significant differences in electronegativity between the carbons and the hydrogens. So you class it as non-polar, and that's very good at interacting with non-polar solvents. So you've got a non-polar region, which is good at interacting with non-polar solvents, and a polar region, which is good at interacting with polar solvents. So this makes them very good solvents because they're good at dissolving most things. So most solids that you want to dissolve in a liquid, if you add this as your solvent, it will work very, very well. Now there are some issues with using halogenoalkanes. There's a branch of halogenoalkanes which are known as CFCs, so chlorofluorocarbons. So they've got a carbon to chlorine bond and a carbon to fluorine bond inside them. An example might be maybe this. So there's a chlorofluorocarbon, it's a halogenoalkane. These are very, very useful. They're used for things like aerosols, they're used for making plastics, and again they're used for the main use, which is solvents. They were used a lot in times gone by, but the problem with them is once you expose them to UV light, you end up forming free radicals. So the main reason is because the carbon to chlorine bond is quite weak. You get this sort of thing forming. So let's imagine we just broke one of the carbon to chlorine bonds for now. So you get chlorine radicals forming where we've broken that carbon to chlorine bond. Hopefully you remember that is homolytic bond fission, so equal breaking of a covalent bond to form these chlorine radicals. What happens when you make these chlorine radicals, so we've exposed the halogenoalkane to light, it's formed these chlorine radicals, they go up and travel on up into the atmosphere. And the atmosphere contains the ozone layer, which is made from O3, so another oxygen-based molecule. The radicals react with ozone this way. And you can see in these steps that you're breaking down. This ozone is being broken down, so it's lost, and in this step again it is lost. Ozone then, breaking down of ozone then leads to things like global warming, so our planet heating up, and then all the various impacts of global warming from that are then caused by these chlorine free radicals. So things like more extreme weathers, rising sea levels, and stuff like that. So the solution to all of this was something called a HFC, which involves replacing the chlorine with a hydrogen. So hydrofluorocarbons this time. So hydrofluorocarbon might be, I'm just making this up, something like that. So you've only got hydrogen and fluorine. Now, because you haven't got the chlorine bond that we had previously, when you expose it to UV light, nothing happens. You don't get as many radicals forming, or any radicals forming at all, and then we don't have the ozone getting depleted by the chlorine free radicals. So CFCs, what was a very useful chemical, their uses are now restricted, and instead people have to use HFCs.